With that, I'm going to introduce our first speaker. This is Dr. Bruce Logan. Dr. Logan is from Penn State University. He has been probably working on this field more than most of us in here. He basically pioneered the idea of moving this into the environmental engineering field. Was one of those first environmental engineers that caught the idea that this could be a very good platform for us to do wastewater treatment. And so that's one of the reasons why he starts our meeting today. So welcome.
Well, thank you very much, and I also would like to add my very, 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 very warm welcome to you all. I was at the University of Arizona in Tucson for 11 years, and after I left Tucson, I wondered if I could ever come back to Arizona again, because I didn't think I could ever face the heat, but I guess I can, because I'm back. So, and it's a pleasure to be here. So today what I would like to do is propose that really to take the next step forward. Is that a little loud? To take the next step forward in this, we really need to start to have commercialized technologies. And with that, shall we say, the research dollars may follow, but until we can get out there and start to show that this can be used in different applications, I think we're going to struggle a little bit. So I'd like to put forward kind of my vision of what the things are that will get us there, and talk about some of the designs and the future for applications. And particularly, I will emphasize for wastewater treatment. So here we have the things, you know, to commercialize. We know what the bacteria are. We know that they continue on and that they, you know, we don't have to do anything special with them. We know we can make materials that are affordable and put them into reactors, and they will produce sustained current. But then we get down to really the nitty-gritty of how do we put these things together? How do we actually get the architecture that is going to be optimal for this purpose? And what I'll come down to at the end, I think, is really when you finally get down to making this work, it all comes down to the cathode. And that's maybe not such a good feeling for many people that want to really be researching the biological side of things, but it's mostly about the cathode. And then I'll end with just a minute or two on thoughts about secondary processes. So I wasn't really going to say anything about bacteria, but when I realized both speakers after me were going to talk about Geobacter, I thought I had to get just a few little words in, because otherwise you'll think we never did research on bacteria. And so this was some work that Matt Yates did as part of his PhD. He said, well, you know, I really want to go out and get some new bacteria, see what's out there, and find out how diverse things are. So he went out to a bog and went to a wastewater treatment plant, used a whole series of methods to look at what was growing up in the microbial fuel cells. And it came out to be pretty boring. In triplicate reactors, they were almost all delta proteobacteria, and all those delta proteobacteria, they were Geobacter sulfur-reducens. And it didn't really matter where we started. This was the wastewater and this was the bog. By the end of a few cycles in the reactors, they were all Geobacter. And so we said, well, maybe it's how we run it at the potentials. So we set different potentials. This is some work we did in these air cathode reactors. And again, it got pretty boring. It's mostly delta proteobacteria. It's mostly Geobacter. So it's, okay, it's Geobacter sulfur-reducens. But what about when the media is complex? Well, there's a lot of other things in there, but you still end up with a lot of Geobacter. This is some work done by Sunichi Ishi, who was at Craig Venter Institute at the time. So fine, okay, it's Geobacter. It's all Geobacter sulfur-reducens, 100% match. But when you actually take the microbes out of the reactors, you find some very startling things. While the 16S RNA shows a 98% similarity, when you do DNA-DNA hybridization, you should get something greater than 70%, but you get less. This Geobacter tolerates very high salt. It grows perfectly fine in 200 millimolar phosphate buffers, where PCA does not grow well. And so when you actually look at what's in your reactors, it's not, at least in terms of what it can do ecologically, the same. So I'm not saying that we're wasting our time studying Geobacter sulfur-reducens, but you ought to look at what's really in the reactor. And Dan Sun's done some nice work. This will be a talk tomorrow showing how the biofilm changes in viability, conductivity, and what the implications of that are for producing current. So let me get to my central theme now. These are a list, this is photos of several reactors that have been produced. This was the first one, large-scale reactor in University of Queensland did, some others in China. And the question is, you know, where does all this architecture go? How do we best scale these things up? We know we need to do it cheaply. This was a couple of studies done several years ago now saying, well, we got to do it for less than $100 per square meter, but it doesn't tell you how that square meter is actually in the system. When many of us got into this, we thought, well, this is going to be really easy. We just build one big tank with a lot of anode in it, and one big tank with a lot of cathode, and then we connect them up and everything will be fine, right? And of course, it doesn't work like that. But yet, in 2003, they're still showing papers where there's one big tank of anode and one big tank of cathode. We got to stop doing that, because you can't just put the anode in one tank and the cathode in another. So I want to talk about how we can think about the design from the perspective of surface area of cathode per volume. And this is, the talk's really building off of a recent literature review paper that we did. And I want to say that there's the materials. We know a lot about the materials now, whether it's flat or brush or granular or whatever. We're going to have an anode, we're going to have a separator, we're going to have a cathode. And the first thing we need to do is decide, is it going to be a plate and frame, or is it going to be tubular? And if we make that decision, how much electrode density can we put into the system? So first, let's look at these tubular systems. These are all different tubular systems. This was that first one I mentioned. This is another one here. This is one that we did in our lab. This is Zhen He's reactor in Virginia Tech. Here's what it comes down to. If you decide you're going to do a tubular reactor, you have a certain amount of area of that cathode per volume of reactor. And since it's a cylinder, you do the geometry, that area of the cathode scales as one specific area, square meters per cubic meter, or 1 per meter, is 4 over the diameter. So all you really need to do when you do a study is say, this is the diameter of my tube, and then you're done. We know a lot about it once we know that, but nobody ever does, or it's rarely ever done. So what did the University of Queensland choose? They chose a diameter of 18 centimeters, which ends up giving you 22 square meters per cubic meter. How well did it perform? Well, we don't know. They never published it. They've talked about it at these conferences. But basically, it produced about 8 watts per square meter, 8 watts per cubic meter. Oh, great, typo right there. About 300 milliwatts per square meter, which is not bad, but it was running on a very concentrated brewery wastewater. This is Zhenha's reactors. They're these small tubes. And he's taken the approach that we make these small reactors, and we use a lot of them. The diameter of that is 5 centimeters, so that gives you 80 meters squared per cubic meter. They had an 11-hour HRT. They produced about 10 to 50 milliwatts per square meter, but it was domestic wastewater. Final COD up around 100 milligrams per liter. A more recent study, this just came out in the past month, 80 square meters per cubic meter, but because they're trying to remove a lot of the COD, there's really not that much power that ends up being generated per area. So you have a high cathode surface area, but if the COD gets low, you don't produce a lot of power. This other design was kind of interesting because it's also tubular, but if you have all these tubes together, you can't, from a perspective of connecting the fluid, you would all have the same fluid within the reactor, therefore all the electrodes would have the same potential. Instead, what they did was to actually have a little tube connecting these sequences, and thus these are individual reactors. And their design ended up giving you 62 square meters per cubic meter. I don't remember what the HRT was. I'm not sure it was that clear. They got about 60 watts per square meter. Another variation on the tubular reactor, and this is somewhere in between. Ziyang Ren was doing this, and I said, well, is it a plate or is it a tube? Because it's a flat reactor that's wound in a tubular configuration. They didn't test domestic wastewater, but they had some designs which gave them basically about 100 milliwatts per square meter, but they were using percarbonate, not oxygen. So how does that compare up now to the plate and frame designs? So this was our plate and frame, the very first one, it was just 2 electrodes bolted together. And that reactor had about 25 to 28 square meters per cubic meter. It allowed us to look at reducing materials costs. And so we proposed to create an architecture essentially out of this reactor. But the scaling factor here is based on the width of the anode and the cathode. So the specific area, square meters per cubic meter, ends up coming, what is the distance of the cathode and the anode in a repeating unit? If you have 4 centimeters for this, it's 25. If you have 8 centimeters, it's 13, and so forth. So this was our design, and we ended up with a low specific surface area per volume. But why not go to something higher? So Hong Liu's reactor was at 680 square meters per cubic meter. And so they were able to get kilowatts per cubic meter. But the interesting thing here is that their reactor was 30 mils and ours was 25, and yet they had that much more specific surface area. Now you can't really use that for wastewater because it would clog up very quickly. So what we did is we looked at the range of power densities we were getting based on the size of the reactor. And these are, by definition, microreactors. These are sediment fuel cells. These are MFCs that are treating wastewater. And then in green are the MFCs using acetate solutions. And when you look at the volume, as the volume gets bigger and bigger, you can sort of see this trend with the acetate studies. These are log scales of getting smaller and smaller in terms of how much cathode area you put in that reactor. And that's not, I think, where we want to be. We want to really be trying to scale up consistently as we get larger. And in fact, with the MFCs treating wastewater, there doesn't seem to be a good sense of how they're scaling as they get larger. Most people that have been going to these larger systems are actually using acetate. And if you break that down a little bit more, I've pulled out all the data except the wastewater MFCs. So that's, go back. So the MFCs that are on acetate are green, and the ones on wastewater are blue. And so you can see the green ones here, and as you get out here down on the blue ones, you know, these larger ones tend to be lower cathode specific surface area. So we really need to build these things with more cathode area per volume, but we can't use too much, and that goes back to an earlier study that we did where we showed that as you got these electrodes too close, you got oxygen leakage through the cathode, and so power went down rather than up. So electrochemically, you'd say, well, the closer I get those electrodes, the more power I should be able to produce, less solution resistance, but the power went down, and it was oxygen contamination. Well, that was done with flat electrodes, which hold a very small amount of biomass and can easily become aerobic. So the question was, well, if we went to a 3D electrode, can we avoid problems like that? So are these brush electrodes able to avoid those problems? This is Adam Hutchinson's work. He took a brush electrode and he started trimming it, and he looked to see where power dropped. And these are in different solutions, but you can see as the brush was trimmed more and more, the power didn't really decrease that much. You got down to almost something that barely even looked like a brush before that power really dropped off. So that was good. We thought, oh, this is great. This brush is doing really, really well. We can use really small brushes. So, oh, and we also, this is work done by Sarah Hayes, and she showed that with the brush electrode, this is over about 100 days, the power with wastewater was very stable. But with these flat mesh electrodes, it eventually dropped off if we got them too close to each other. So that was good. We said, all right, we need to use these brush anodes. We can get them close to the cathode, and it should all work great. So Vanessa Alanis said, well, let me look at a few big electrodes, few more smaller ones, and then some tinier ones, and see how that electrode size matters. This is very practical stuff, right? So she found if she went to these smallest electrodes, so this is the big one, smaller one, smaller one, but she kept it close to the cathode, produced good power. So up around 1,000, about a watt per square meter, whereas if it's away, it goes down, that's electrochemical resistance. So we figured, okay, we're done. We use small electrodes. We pack them in really tightly, and we're done. But this was done with acetate. And so when we actually went and built these reactors but tested them with domestic wastewater, we failed horribly. Well, not horribly, but it wasn't so good. Because when those brushes were small, we had exactly the same problems that we had when we had those thin carbon paper and carbon cloth electrodes. The wastewater strength was not high enough to make sure that all that oxygen got consumed before it leaked in the reactor. So the anode potentials would become positive, it would become slightly aerobic, and the reactor would fail. So we can use brush electrodes, and in fact we need 3D electrodes, but they can't be too thin. So where does that leave us in terms of scaling up the concepts? Well, this was what I'll call our generation 01, where we looked at going from flat electrodes to brush electrodes and testing this reactor spacing. Then we went to what I call the generation 1, which are these multi-electrodes. So this is one anode, one cathode. Then this is multiple anodes, one cathode. Gen 2 was now to start to use 2 banks of each of these, and then Gen 3 is a whole array of these, and I want to talk a little bit about that now. So with these Gen 1 reactors, these are 3 anodes, and we looked at having this separator assembly here and no separator. So this one, we have a separator which can cut oxygen down, but it also reduces proton transfer between the anode and cathode. Whereas this one is very, very close, doesn't touch it, but it has no separator to impair power. And what we found was that the maximum power we produced in this was pretty similar. But the maximum power doesn't tell the whole story. And what the whole story was that this reactor without a separator fouled too quickly. So we realized we needed to have a separator in the system. And if we're going to have a separator, once you do it, the question is, do we go to this configuration or this configuration? And if you go to the one where it's not touching the electrode, maybe you have, in a modular design, you have 2 cathodes. One cathode on this side, one cathode on the other side. So we looked at comparing these 2 designs, and I won't go into the details of that too much because Kyung-Yeol Kim is going to give a nice talk on this on Saturday. But here's the other thing I want to point out. We're thinking so much about the electrochemistry and so much about cathode area per volume, we forgot one other thing, which was how well we removed COD. And when you actually measure the actual hydraulic retention time, not the theoretical hydraulic retention time, but actually putting a tracer through there and looking at how much time the wastewater spends in there rather than theoretically based on its volume and the flow rate, we found these 2 reactors produced exactly the same amount of COD removal. So in terms of COD removal, it's the HRT, the actual HRT, not the theoretical HRT that matters. These other designs can really affect how much power you produce, but they don't affect the COD removal. So with our Gen 2 design now, what we're trying to do is to create something that's truly modular, that is not in what was called a cassette design, where you bolted an anode and a cathode together, but rather you can individually address a bank of anodes and a bank of cathodes. So this is a whole series of anode brushes. This is the cathode, then another series of anode brushes, the cathode, and so forth. And these individual modules you can pull out, push in, so they're easy to manufacture. You can slide them into the reactor, and if you need to clean the brush anode or something, you just take the module out and hose it down and snap it back in. We tested these reactors. The volume was about 1.5 liters. So about, depending on whether you use the total reactor volume or the liquid volume, and I would argue you want to use the total reactor volume because that's what the engineer is doing, trying to decide how big the tank is. And so that's about 20 square meters per cubic meter. So here we looked at the power produced from the bank of anodes on the left, and then the power produced by the anodes on the right. And you can see the power density curve is quite close for both of these anodes banks. So that's a good sign. It means that we're getting good flow through the system. This produced up to 400 milliwatts per square meter, which is, I think, about the highest for a low-strength domestic wastewater. This is like 300 or 400 or 500 milligrams per liter of COD. In fact, here's the influent COD here. This is the effluent, the voltage generation, and this is pretty normal when you're dealing with wastewater. Your voltages are going up and down because the wastewater strength is not always homogeneous. In a fed batch system, you can see the time to get all the COD out, so this is most of the COD, goes from about 20 hours up to about 60 or 70 hours. But you can't afford to do that in a wastewater treatment, and I would argue that you don't want to try and do that. You don't want to get all the COD out, because if you do, there's going to be no electricity generation. So this gives us sort of a, certainly not a complete summary, but a snapshot of where we are in terms of domestic wastewater. If we're going to set these up and do domestic wastewater, sure. If we put acetate in our domestic wastewater, we can say we can make a watt per square meter. But if you really have domestic wastewater in batch, at the beginning of the batch cycle, you maybe get 400 milliwatts per square meter. If you run it in continuous flow, about 200 or 300 milligrams, 300 milliwatts per square meter. And compare that to some other studies with some of these other reactors. Several of these studies are our own lab. These are a couple cassette reactors by others. I think we're doing pretty well. So what we can say is we can make a reasonable amount of power. We can get the COD down, but not completely removed, make it work. So let me finish up with just a couple thoughts here. I think there's plenty of data out. I started showing some of the reactors where they had either good COD removal and not much power, or they had good power but not much COD removal. I think what we have to do is realize if we're going to use wastewater treatment, we can't get all the COD out in a microbial fuel cell. It's ultimately going to fail to make very much current. We're just going to have a passive aeration system. So we're going to need a second process. We need to start working on that more concertedly, and we need to remove the nutrients, but I'm not going to tell you how to do that today because I don't know how to do that. It's always going to be a battle. If we just have an air cathode here, the air that leaks through is going to remove COD at a certain rate. If we generate current, we can accelerate the rate of COD removal and hopefully lessen the amount of COD that goes to aerobic removal of COD. But we come down to this. You come down to the point where as the COD gets lower and lower, this is work done by Xiaoyuan Zhang, that you get to a point where the current rapidly drops off. And it drops off here. Doesn't matter what the resistance is, whether it's acetate, whether it's wastewater. You get down to about 100 milligrams, 200 milligrams per liter, and the cells just don't have the ability to create current at those low CODs. So we got to figure out how to remove the rest of the COD. We've been working a little bit with the AFMBR. It's actually an idea that was pioneered by Perry McCarty at Stanford. We've just used it to add on to our system. And with that, the second process basically recirculates GAC around and knocks on the membranes stonefoul. You can produce an effluent COD, which is less than 30 milligrams per liter, and a very high removal of solids. This would allow us to not need to have clarifiers. The low energy demand of this system hopefully could be sustained by the MFC energy output. So with that, I want to conclude. I want to say that I think the work, the community that we've all done has shown us that there are many designs out there. When we really come down to designing these systems, whether they're tubular or they're plate and frame, we have to come down to this central design factor of square meters per cubic meter. We have to not have too little square meters per cubic meter, or the reactors will be enormous. We can't have too much square meters per cubic meter. We can't have 100 or 1,000 square meters per cubic meter because it'll clog in a heartbeat. We need to design the reactor with reasonably cost materials. We think we mostly have that now, and we can design it with a good flow through, good hydrodynamics to give us the HRTs we need. We're going to need to add on the second process. We should put more work into that. Maybe it's not a microbial fuel cell topic, but ultimately it's part of the success of our reactor system. I want to end by thanking my current research group at Penn State, and there are a few of them here today. Wulin Yang will be talking about some work in cathodes, and Yasmin will be talking about some work on electromethanogenesis, work we've done with Alfred Sporman at Stanford, and Kyung-Yo Kim will be talking about the Generation 1 reactors and COD removal and AFMBRs. And I'd like to acknowledge many of you actually in the audience as collaborators and visitors and places that I've been to and worked with. Particularly, I'd like to acknowledge KAUST for just an incredible amount of funding over the years. And I'll leave you with just the thought that I'm the editor of this journal, so I couldn't resist a plug for the journal. Thank you very much.
Return. So we have time for a few questions, and if you notice, there are two speakers on each side of the room, so if there's any questions, please come over so that we can record the question as well.
Bruce, you talked about area to volume as a scale-up parameter. Mm-hmm. How about some of the other parameters for scale-up related to either space velocity or mixing, mass transfer? Have you considered, and can you extend your work that you've done to think about those?
So far, we've just really been able to tease out this the actual hydraulic retention time versus what we thought was the hydraulic retention time. The second part, and we've done this a little bit with these modular reactors, the question is, do you divide up the flow 50 times and put them through each chamber, or do you go through all 50 of them in serial? And I don't think we have a good answer for that yet. I think it's a very reasonable question. We don't know. Should we flow it really fast or really slow, and how's sedimentation going to affect that, and how do we deal with some of the particulate BOD? We can't really get at those until we build that next scale, I think.
So usually in biotechnology, you have, like, say, turbine blade size or mixing ratios as scale-up parameters for aerobic reactors. So maybe we have to come up with something like that for MFCs.
Yeah, I think there will be other design criteria, but for right now, at least I would argue that that's our main one. Don't build too big a tank with one tiny electrode. Don't build a massive electrode in a very small space.
All right.
Ah,
Besides-
Cornel, okay.
A little challenge.
Yes.
Just to think about it, I mean, how useful is it actually to focus a lot of it?
Thank you. Next question. Oh, sorry.
That's what you use that coast funding for. How useful is it actually to focus on domestic wastewater from the perspective that a utility that treats domestic wastewater first and foremost has to treat water and reach sanitation standards, and so that water really has to be cleaned, while an industrial wastewater, typically on an industrial site, there's a lot of similar wastewater. And on an industrial site, this is where you try to get as much out of it as possible, and then you discharge in the sewer, and it goes more into a conventional process. Wouldn't it be better to shift more towards industry? It's an open challenge.
I guess I would not, I will use the double negative. I would not argue that it is not a good idea to, it is a good idea certainly to work with. In fact, they'll be the early adopters, they'd have to be. Anybody that can shave off most of the BOD before they send it to the publicly owned treatment works in the US has a real benefit. The reason I focused on the wastewater is I think it highlights the greatest challenges in dealing with this system. And you really see why acetate doesn't work after a while when you go to something that's incredibly variable like a wastewater. And even at an industrial site, you could have quite high variability. So I would say it's the most challenging, and it's also probably the thing that's most needed in the world, rather than just for a few industries.
Okay.
Ji Yang from University of Colorado. Following up on Cornel's question, there's the second challenge is, should we consider a second product rather than electricity? I mean, we have all these MXCs, all different very good products, and when we look at the life cycle assessment, economical assessment, there are other products might be more feasible, but that might be case by case. I just want to get your comments on that.
Well, I think Cornel and I wrote a paper showing, yeah, if you can produce a value-added product, you're much better off. So the question is, can you do that? And what are the challenges for that? And I would say for right now, we've got good current densities, we've got good COD removal rates, we've got good oxygen catalysts for oxygen reduction. We don't necessarily have the same thing for, say, hydrogen evolution, and we're just starting to understand maybe methane evolution from electrodes. So what would that product be? And if we could figure out what that product is and we can produce it at a high enough rate, then absolutely it would be wonderful. This is essentially turn the wastewater treatment plant into a power plant, but turn it into a chemical factory to produce a value-added chemical that would be even better, more economical, if we could do it.
So our last question.
Hi, my name's Doug Hodgson from the University of Surrey in England. Fascinating talk. You said that you can't get complete COD removal in one fuel cell. I was wondering what your thought is about using hydraulic cascades. So I would have thought eventually, with enough fuel cells in cascade, you would achieve that.
Yeah, so the question is, why not just have two MFCs in series, have the first one make a lot of electricity and have the second one not make too much? Because ultimately, you run into that graph I showed where as you get below 100, you just don't produce anything. And essentially what you create is an aerobic biofilm that's removing all the COD. And you just really, it's not worth the money to build all those electrodes just to have a passive aeration system of the wastewater. So, yep. Okay. All right. Thank you.